Okay, so in this video we will talk about linear independence. Linear independence. Linear independence of what? Linear independence of the spanning set we have seen previously. Okay, and this will lead us to the concept of a basis. So all these topics are well connected together. Let's start with a lemma. Lemma. Okay, we have a okay. So where V is a vector space, S is a subset of that space. Okay, and V is an element. V is an element of that space. Then we have the span of S union the vector V is equal to the span of just S if and only if the vector is already in the span of S. You see? Let's say we have a subset S and we have its span. Its span is the linear combination of the element in that S. So if we have a vector S that belongs to the span of S, then the union of that subset S and V, their span is just going to be the span of S. You know what I mean? That means SV is already in the span of S. So adding a vector that is already in the span of S does not make the span any bigger. Actually, that is what the lemma means. Is that okay? So let's continue. Corollary. So for V, an element of S, okay, omitting that vector does not shrink the span S, which is, okay, so we have, we want to take S, V from S, okay, it won't shrink the span if and only if V is dependent on other vectors in that set S. You see, so previously the lemma is when we add V to S. It doesn't do anything to the span if V is already in the span of S. Here, we are saying that if we remove V from S and we take the span of that new set, S minus V, then we still have the set, the span of S, if we can write V as a linear combination of the vectors of S. So we don't do anything to the span of S. If V is dependent, that means can be written as a linear combination of the vectors of S. Okay. So now let's go to the definition. Definition. In any vector space, a set of vectors is linearly independent if none of its element is a linear combination of the other elements from the set. Okay, so that is what linear independence means. So if you have a vector space, a set of vectors from that space are said to be independent, means if we cannot write any vector as a linear combination of the other vectors. Okay. Now let's have a look at this lemma. This is a very beautiful lemma we call linear independence lemma. We are going to be using it a lot. Okay, so lemma linear independence. Okay. Okay. A subset S of a vector space is linearly independent if and only if among its elements the only linear relationship C1 S1 plus C2 S2 plus Cn Sn, okay, equals to 0 is the trivial one. That is C1 equals to C2 equals to Cn equals to 0. So where Si is different from Sj, when I is different from j. So basically, a subset S is being called linearly independent if the only time we can take the linear combinations of its vectors is when the scalars are 0. So that means the set is linearly independent. That means we cannot write any vector as a linear combination of other vectors. Okay. So let me continue with the lecture. We will do a tutorial where we will do the calculation. This lemma is important for calculation. So to be able to prove that the element of a set is the element to be able to prove that a subset if it is linearly independent, we are going in the calculations in the tutorial, we are going to take the linear combination of the element of that subset and let it equal to 0, perform Gauss's method, and prove that actually the C1, C2, Cn's are 0 in case the subset is linearly independent. But if all the C's are not 0, then the set is not linearly independent, is actually linearly dependent. Okay, we will see that shortly in the tutorial. We will do more theories here. So we have a corollary. Okay, let's continue. So we have a set S is linearly independent if and only if for any V in S its removal shrinks the span S. So the new span is going to be included in the big span. Okay, so I think this makes sense. We have said that a subset is linearly independent if no vector can be written as a linear combination of any other vectors. So removing that vector from the set is going to shrink the span of the set, of the new set. Okay, so let's continue. 6 lemma suppose that S is linearly independent and that V V is not an element of S. Then the set S union V is linearly independent if and only if V is not in the span of S. So we say, let's say, suppose you have a set S, which is linearly independent, and V is an element of that S. Then the set S union V is linearly independent if V is not already in the span of S. I'm sure that makes sense. Okay, let's continue. Okay, 7. Love these corollaries and the lemmas and the theorems. They are so beautiful, right? Okay, number 7. Let's do corollary. In a vector space, okay, let me split the board into 2. Any finite set has a linearly independent subset with the same span. So if you have a vector space and we have a finite set in that vector space, then it is linearly, okay, so that a set has a linearly independent subset within the span. Okay, let's continue. Okay, another corollary. We have a subset. Let's say we have a subset S, which is a collection of S1 until we have Sn, okay, of a vector space. Okay, so this set is linearly dependent, okay, the opposite of independent, if and only if some SI's is a linear combination of the vectors S1 till Si minus 1. Okay, listed before it. So basically what it means is the vectors in a set are linearly, okay, a subset is linearly independent, is linearly dependent if a vector can be written, a vector of that subset can be written as a linear combination of other vectors of the set, okay? That is basically the opposite of a linearly independent set. So 9, let's finish this lecture with the following lemma. The lemma says any subset of a linearly independent set is also linearly independent. Wonderful. So any subset of a linearly independent set is also linearly independent, and any subset, and so let me see. This is the first point. The second point, any subset of a linearly dependent set is also linearly dependent. I think this is a superset, not subset. This is not subset, so I think this is superset. Any superset, okay, of a linearly independent set is also linearly dependent set is also linearly dependent. So let's do, okay, now let's summarize some of these lemmas and corollaries. So let's do some summary about dependent and independent sets. So let's say we have a subset S or a set S, which is either independent or S is dependent. Okay. Okay. And let's suppose we have S hat, which is a subset of S. Since S is already independent, any smaller set taken from S, any subset of S, is going to be independent as well. S hat must be independent. Okay? But S hat, when S is already independent, if we take a subset of S, the subset can be independent, either independent or dependent. So it may be either. Okay. Now, let's assume that S hat is a superset of S. Okay. Then, if S is linearly independent, then S hat may be either, can be dependent or independent. Maybe either. But if S is already dependent, then S hat, a superset of S, must be also dependent. Okay, so I'm going to stop here, and in the next video we will do the tutorial about how to prove that a set is linearly dependent or independent using our beautiful lemma about linear independence. So we are going to use this lemma to do the calculations. Is that okay? Okay, see you in the next video.